It is trendy these days to accuse critics of misinformation and pseudoscience. What is pseudoscience? How to distinguish this from contested science? And which is the valid normal state when the scientific method is still running its course and key issues are not yet fully understood? And why are the so-called experts and the scientific authorities themselves often so resistant to new ideas? In this video, we explore these questions using the famous case study of Dr. Ignaz Semmelweis, the pioneer of antiseptic practices. We will then end the video by reviewing how the concepts you have learned so far help you to ask the right questions and seek the right answers, an increasingly important skill in a complex world, where actions and policies are being pushed in the name of science. The modern-day philosopher Karl Popper thought about what science is and what science should be. In his view, scientific theories can never be completely certain. In fact, one may argue, as did physicist Werner Heisenberg, that what we observe is not nature in itself, but nature exposed to our method of questioning. He was referring to the notion that the act of measurement itself determines which aspect of nature is revealed. This is a fundamental feature of quantum physics, but let us leave this for now. What Popper intended was to dispel an absolutist, dogmatic attitude towards scientific theories. He argues that good science must be falsifiable. This means the hypothesis or the model must make predictions that have the capacity to empirically tested and be proven wrong. Any theory that cannot be empirically tested nor proven wrong in this view is not science. That is pseudoscience. Pseudoscience is a derogatory term that you can stick on a theory or your opponents that claim to be science or doing science but is in fact not. A short story of Sigmund Freud and Albert Einstein would illustrate the principle of falsifiability and explain why Popper developed his criteria. Freud was a psychoanalyst who developed the seduction theory in mid-1890s to explain that mental health problems are all due to early childhood sexual abuse. Some patients recounted such incidences, although many of them were later found to be false. Most patients, however, do not even recall such abuses. Freud, however, then posited that this must be because they have been repressed into the subconscious. He argued that the best proof is in the symptoms themselves. Thus, Freud is able to explain the symptoms of any patient after the event by associating it with abuses that must have occurred earlier. This seduction theory can never be falsified, and Popper had much disdain for this type of science. On the other hand, he notes that Albert Einstein, the physicist, conducted his work in a very different way. In 1915, Einstein put forth his theory of general relativity that posits that the gravity between masses arises from their warping of space-time. This theory predicts that light would be bent by gravity through a specific amount. As a result, the apparent position of stars will be shifted in a predictable way when starlight passes close by the sun. This theory can be tested. If the predicted shift cannot be found, the theory is falsified. 4 years later, In 1919, Arthur Eddington and Frank Dyson made careful measurements during a solar eclipse and found that the predicted shift do indeed occurred. The apparent positions of the stars were displaced by the sun, depending on how close starlight passes next to the sun, exactly as predicted by theory. Subsequently, other scientists were able to make even more precise measurements to get even better agreement with the theory. Thus, general relativity is accepted as correct. Popper described what Einstein did as science and what Freud did as pseudoscience. Pseudoscience looks to the past for confirmation, while science looks to the future for disproof. We will further explore differences between these and between established science, unsettled science in a subsequent video. Thus, summarizing, in Popper's philosophy, scientific theories must be falsifiable. Scientific theories can never be completely certain, and science should always seek to disprove. The key message here really is that to adopt a healthy skepticism and be willing to discard old methods for better ones. This philosophy is embedded inside the scientific method, through which hypotheses and models are always continually challenged by experiments and observations. Popper's philosophy has also applications beyond science. This philosophy suggests we should all continually challenge our innate assumptions and adopt a healthy skepticism of received wisdom. We should be receptive of ideas and knowledge that may not align to our beliefs, and we should be willing to discard beliefs and revise our position in the face of evidence. This is the opening of the mind of scientific questioning and critical reasoning. Occam's razor. Let us return to the example where you couldn't access website on your laptop. Suppose you tried to access a second domain and failed. You tried a third and a fourth, but you couldn't view any of the web pages. Which of the following is more likely to happen? 1. The 4 domains are simultaneously down at this time. Or 2. Your laptop is not connected to internet. You would say 2, right? This is the essence of Occam's razor. William Occam is a philosopher and theologian who lived in late 13th century. A popular statement of Occam's razor, named after him, is, "The simplest explanation is the best one." While the statement may not be exactly what he wrote or meant, it nevertheless provides a powerful principle to guide scientific and other thinking. In philosophy, razor is a principle that allows one to shave off unlikely explanations for the phenomena or to avoid unnecessary actions to reach a goal. William believed that plurality should not be posited without necessity in matters pertaining to his faith. In other words, ideas should be kept simple to the extent possible. One should not add more rules than necessary to regulate behavior. One should not add more complexities than necessary to explain something. Applied to science, this would mean, if there are competing theories that could explain the data equally well, the simpler theory is the better one. However, this philosophy is only a guide to choose between competing hypotheses or models that make similar predictions. It does not mean that the simpler theory is the correct one. For example, in the time of Newton at the end of 17th century, it is simpler to imagine that light travels as particles in straight lines, bouncing off surfaces, than as waves fanning out in all directions, which is more complicated. However, Thomas Young at the beginning of 19th century showed conclusively that light has wave properties. Light diffracts and forms interference patterns, something only waves can do. Then 100 years later, at the beginning of 20th century, Albert Einstein showed conclusively that light has particle properties. Light is absorbed and emitted as particles. Today, we accept that light is a strange creature, behaving as both particles and waves, which remains mind-boggling even to physicists to this day. Despite the shortcomings of Occam's razor, it turns out to be useful again and again. One such example is the development of models of the heavens. In ancient times, the earth was perceived as stable and unmoving. Looking up to the sky, one observes the sun and the moon and stars moving across the sky from east to west during the day and night respectively. This is natural to assume that the heavens move in simple celestial spheres around the earth, which is the center of universe. Then it was realized very quickly that different bodies don't all rotate around earth on the same axis. So there must be multiple celestial spheres. The sun moves on a different sphere than the moon, which in turn moves on a different one than the stars and each of the planets. Then it gets more complicated. Careful observations show the planets, so-called wanderers, periodically reverse their direction of motion in the sky against the backdrop of stars before resuming original trajectory. Thus, the planets must also spiral in their orbits. And it gets worse. As more careful observations were made, more deviations were found and more complexity had to be added to describe the motion. Eventually, it became a terrible mess. 1,000 years later, Nicolaus Copernicus presented a heliocentric model in which Earth, together with the planets, orbit around the Sun. This restores the simplicity and elegance of science and explained all the complicated motions observed. But nobody accepted this model. Nobody believes that something as massive as Earth can move. It had to wait for another 200 years before Galileo Galilei, using his newly invented telescope, found that planets indeed show phases relative to the Sun, just like the Moon. This supported the Copernican model. Further work by other astronomers and physicists eventually convinced scientists that Earth indeed orbits the Sun. Thus, despite resistance at first, the heliocentric model, which can explain the same observations in a simpler manner, was eventually accepted into the mainstream. Occam's razor turns out to also be a useful philosophy for data fitting. You may already have encountered data fitting in your data literacy classes. Let's consider a data set like the ones given by the red dots here, plotting a dependent variable y against an independent variable x. You want to first find a best empirical fit to this data. You have no theoretical guide to the functional form of the equation. You can only guess. Do you fit it with a straight line? If you do, however, you will find that the fitting does not reproduce key features of the data. The J-shape of the data is not given by the straight line. In other words, the data is underfitted. The fitting equation is too simple, only two parameters, A and B. This is not sufficient to describe the data. You may try a more complex equation, a quadratic equation, with three unknowns, A, B, and C, to be determined. You can see a good fit. The fitting describes the key features well within what you believe is noise or random errors of the data. You will learn more about random errors in another video. However, you may try even more complex equations. For example, here a ninth order polynomial equation with 10 unknowns from A to J. Surely you have got a better fit. The fitting line now passes even better through all the data points, including all the little wriggles. Is it really a better fit? The answer to this question depends on whether these wriggles are real. They may not be. They may just be noise or random errors. If each wriggle is anchored by only very few data points, they are likely to be noise. If so, this better fitting here is simply following the noise. We say the data is overfitted. This is where Occam's razor helps. It suggests that we should not use such a complicated equation. The simplest model that can follow the trend is the quadratic one. In summary, Occam's razor does not imply that the simplest model is the best, but the simplest one that is appropriate for the situation. The straight line is the simplest model, but it doesn't describe the data well. In other words, the simplest model that describes the data with fewest parameters is often preferred, so long as the fit is good. The history of science is checkered. Predictions are made by theories, often informed by experiments or observations. Further experiments or observations may either support or dispute them. The theories then get refined. Sometimes when they get too complicated, a simpler theory with similar or better predictive power may emerge. When this happens, science is revolutionized. Occam's razor serves as a convenient heuristic for scientists to test models and also for non-scientists to make decisions. We end the video here, following the advice of William Occam. We say, keep it simple.